In this video, we're going to conclude our study of Gauss's law. We'll look at what happens when you put a conductor in an electric field, and also we'll look at charged conductors. In addition, we'll look at some further problems using Gauss's law. So let's look at what happens when you put a neutral conductor in an electric field. Here I've got my neutral conductor. In other words, it doesn't have an excess positive or negative charge to start. And the picture is showing that by just showing you equal numbers of plus and negative charges. So what's going to happen when I take this conductor and I place it into this uniform electric field? Well, we know that the force on a charge is equal to the charge times the strength of the electric field that it's placed in. So in other words, since it's the electrons that are free to move in a metal, what's going to happen is the electrons are going to move in a direction opposite to the field because obviously they're negative charges. And so we'll start getting an abundance of electrons over at this end of the conductor, and of course that will leave this end of the conductor positively charged. Again, overall it's still a neutral conductor, but we now have a charge separation. Notice that that charge separation is going to result in a new electric field within the conductor that's opposite to the direction of the electric field that the conductor's been put in. So in other words, our negative charges are going to move over here, leaving us positive charges here, and that creates an electric field to the left. So when will the charges stop moving? Well, they're going to stop moving when there's no longer a force on them. And remember, if there's no longer a force on a charge, it means there's no electric field inside that conductor. So in other words, the electric field that gets set up by the charge distribution is exactly equal and opposite the electric field that the conductor is being put in. And so once those electrons are no longer moving, once we've reached electrostatic equilibrium, the electric field inside that conductor must be zero. That's an important point to remember. I'm going to put a box around that, and you'll notice it's bold. So that's important, that the electric field inside a conductor is always zero in electrostatic equilibrium. By the way, the reason we specify this is obviously you can have an electric field inside a conductor, like in a wire carrying a current, but in that case the charges are moving. Here we're looking at a static situation. Once the charges have distributed, they're no longer moving. The electric field must be zero inside that conductor. This helps us to understand why it is that you're safe in your car in a lightning storm, even if you have no rubber tires on the car at all and the car is just resting on the ground. Well, first of all, what happens in a lightning storm is the clouds start getting a separation of charges. So in other words, the top of the cloud becomes negative, the bottom of the cloud becomes positive, and as the bottom of the cloud becomes positive, that induces a charge separation within the Earth as well, so that on the surface of the Earth we have negative charges and positive below that. You'll notice that gives us an electric field between the bottom of the cloud and the surface of the Earth in this direction. So we've now got an electric field, and if that electric field is strong enough, we can get a bolt of lightning. Now, think about your car. Your car is essentially a conductor. And so what we know is that here you are inside your car. Well, the electric field inside that conductor, even though that conductor is in an electric field, the electric field inside is going to be zero. And so that's why you're protected inside your car. Now, even if we do get a bolt of lightning, that bolt and the electricity that it contains will stay on the outside surface of the car and eventually get down to the ground. And in fact, this is why the rubber tires don't help you, because if the lightning bolt can get all the way from the cloud to your car, it can certainly get from your car down to the ground, and that's in fact exactly what happens. Let's now look at charged conductors. So let's say we take a conductor and we put a net charge on it. So it's either got more electrons than protons or more protons than electrons. So it's got a net charge on it. Even in the case that we have a charged conductor, the electric field inside the conductor in electrostatic equilibrium is always zero. That's important. And again, we're only looking at the static case here. So if I take a conductor and I dump a bunch of charge on the surface, it will distribute in such a way that the electric field inside is zero, and all of the charge will reside on the outside of the surface of the conductor. Okay? I'm going to put a number of stars on this slide. That's really important, as we'll see, to understand when we do some problems. So a conductor in electrostatic equilibrium, even if it has an excess charge on it, the charge will always reside on the outside, and the electric field inside that conductor everywhere is zero. An example that utilizes this concept is the Van de Graaff generator. We have one of these in the classroom, and I'll demonstrate it for you next time we meet. But basically, a Van de Graaff generator is a very simple device. We have this conveyor belt here, which is essentially just a rubber band. And basically, it's an insulator, so we put charge on the insulator. The insulator gets carried up the belt. We've got a motor here driving the belt. And then at the top, that charge is removed and distributed to the inside of that metal dome. Well, what does the charge want to do when it gets to the inside of the dome? It wants to immediately get to the outside of the dome. And so what happens is we keep building charge up on the outside of the dome by dumping it on the inside and then it moving to the outside. And this allows our Van de Graaff generator to get to a very high voltage, and in fact to a high enough voltage that we'll start to get sparks. We're going to talk much more about this in our next unit on electric potential. But just this idea of if you dump charge on the inside of a conductor, it will immediately go to the outside is the conceptual part that we need to understand to see why a Van de Graaff can build up so much charge that it can then create sparks. And by the way, at the Museum of Science, in the lightning demonstration, that is a massive Van de Graaff generator that's being used. So let's do a problem that we need the information we've just learned about the fact that the electric field must be zero inside a conductor in electrostatic equilibrium, even if there's a net charge on the conductor. So let's look at the example. A solid conductor with a cavity carries a total charge of 7 nanocoulombs. Within the cavity is a point charge of -5 nanocoulombs. What's the charge on each surface, inner and outer, of the conductor? Okay, so let's first make sure we understand the picture. This is a shell, but it's got some thickness to it. This area here is nothing, so that's the hollow part. And then you can see we've got a charge placed in the center here. So here's the key thing we need to understand. The total charge on this conductor is 7 nanocoulombs. Now, if there weren't a charge inside here, then all of the charge would just be distributed on the outside. But this problem is more complicated than that. And that's because we've got this -5 nanocoulomb charge right here. So here's how we have to work this problem out. We need to use Gauss's law and think about the fact that we know if I draw a Gaussian surface anywhere inside this conductor, E here must be 0, because the electric field has to be 0 anywhere inside a conductor in electrostatic equilibrium. Okay, so now let's write down Gauss's law. If E dot dA is equal to the charge enclosed over epsilon naught, if E is 0, then E dot dA has to be 0. So what does that mean? It means the total charge enclosed by my dotted line, my Gaussian surface, has to be 0. So because E is 0, Q enclosed must be 0. So let's think about what that means now. the total charge inside my Gaussian surface that I can draw anywhere within the conductor, the total charge in there has to be 0. So that means that if I call the charge on the inner surface Qi and the charge on the outer surface Qo, what we know is that this charge plus whatever on that inner surface has to equal 0. So Qi, and I'm just going to call that charge at the center Q, Qi plus Q has to equal 0. Well, therefore, notice that the charge on the inside surface has to be 5 nanocoulombs because Q is negative 5 nanocoulombs. And that's the only way we can be sure that the electric field anywhere inside the conductor will be 0. Now, any charge that's not on the inner surface we know has to be on the outer surface. Since the total charge on the conductor is 7 nanocoulombs, we know that Qi plus Qo has to equal 7 nanocoulombs. Well, therefore, the total charge on the outer surface, Qo, is 2 nanocoulombs. And so those are our answers. Notice, by the way, the key concept you have to know to get this problem right is this, that the electric field has to be 0 anywhere inside the conductor. Let's look at this problem. Two hollow conducting spheres have a common center at O. A charge of negative 160 nanocoulombs is placed on the inner conductor. A charge of 10 nanocoulombs is placed on the outer conductor. The inner and outer surfaces of the conductors are denoted by A, B, C, and D. The charges on surfaces C and D are closest to. Okay, so I want you to pause the video and try this yourself. Let me just give you a hint, and that is work on all of these types of problems. Work from the inside out. Also notice that in this problem there is no charge at O. Okay, pause the video and see if you can get it right. Okay, so it turns out that the correct answer is D. And let's go through and see how we figure that out using the fact that the electric field inside a conductor in an electrostatic equilibrium is always 0 and using Gauss's law. So as I mentioned, I'm going to work from the inside out. So this is my inner conducting shell. And what I know, therefore, is that the electric field anywhere inside that shell has to be 0. Okay? And so let me go ahead and work here. Anywhere inside that conductor, the electric field has to be 0. So E equals 0 inside conductor. Well, that means that from Gauss's law, the integral of E dot dA equals the charge enclosed over epsilon naught. That means that since E is 0, the charge enclosed by that surface has to be 0. But what is the only possible charge in there? It's the charge on this inner surface, what we're going to call QA. So therefore, since the charge enclosed in my dotted line has to be 0, we know that QA has to be 0. Notice that's different than the last example because here we didn't have a charge at the center. Okay, so now the next question is, what is the charge on surface B? We know that the inner conductor has a total charge of negative 160. Well, that means QA plus QB has to be equal to negative 160 nanocoulombs. But since QA is 0, we learn that QB is negative 160 nanocoulombs. So all of the charge on the inner conductor is on its outer surface, surface B. That's where all the charge resides. And that makes sense because there is no charge here at O. All right, let's move out to the next conductor. Once again, we know that if I draw a Gaussian surface anywhere inside this conductor, we know that anywhere inside there, E has to be 0. And therefore, Q enclosed has to be 0, just as we've talked about up here. Therefore, I know that QB plus QC has to equal 0, because the charge enclosed by my red dotted line here is the charge on surface C and the charge on surface B. We know that the charge on surface A is 0. Therefore, since I know QB is negative 160, that tells me that QC is positive 160 nanocoulombs. Then finally, we know the total charge on the outer conductor is 10 nanocoulombs, so we know QC plus QD is equal to 10 nanocoulombs, because the charge, again, either has to be on the inner surface or the outer surface. It can't be anywhere in the middle. Therefore, QD has to be equal to negative 150 nanocoulombs. And so that's why our answer was 160 and negative 150. Try this question. A particle with the charge of plus q is inside a spherical Gaussian surface, and 3 other charges, one with one with a charge plus q and 2 with a charge negative q, are outside the Gaussian surface as shown. The net flux through the surface is. So go ahead, pause the video, and think about this one. Remember that when I ask you a question about flux, you should smile, because flux questions are easy questions. Remember that the left-hand side of Gauss's law represents the flux. So finding the flux is as simple as adding up all of the charge enclosed in the surface. Well, how much charge is enclosed in our Gaussian surface? It's just plus q. So it's q over epsilon naught. And so all I have to do here is pick the one that matches. Well, q is a positive charge, so the correct answer is greater than 0 flowing out of the sphere. And it's that simple to find the flux. Here's the follow-up question. The same setup, and now I'm interested in what the electric field is at point P. So the question is, could we use Gauss's law to find the value of the electric field at point P on the Gaussian surface shown? Go ahead, pause the video, and think about this one. So this question is really important because it really ultimately shows how much you're understanding Gauss's law. The answer is no. You absolutely cannot use Gauss's law in this situation, because remember, to use Gauss's law to solve for the electric field, we have to pick a Gaussian surface over which we can make the argument that the electric field is constant. Well, you definitely can't make that argument here, because we can't pretend that those other charges aren't there. In other words, our electric field lines might look something like this, but then these are kind of repelling each other, and in other words, the electric field lines are a big mess. They're certainly not constant over the surface of that of the Gaussian surface we chose. So I'll just write this out. E is not constant over the surface. So I can't get E out of the integral. That's the crux of it. So this is a problem where I can't use Gauss's law. Again, remember, Gauss's law can only be used to solve for the electric field in symmetrical situations, and for us those are spherically symmetrical. This is clearly not spherically symmetrical the way those charges are distributed. So if I wanted to know the electric field at point P, I'd have to go back to the way we learned to do it previously before we covered Gauss's law. I cannot use Gauss's law to find that electric field. This one says a cylindrical piece of insulating material is placed in an external electric field as shown. The net electric flux passing through the surface of the cylinder is. So go ahead and pause the video and try to figure this one out. Okay, the correct answer here is 0, and there are a couple different ways you could have thought about that. Remember that electric flux fundamentally is just the way we measure the number of field lines coming in or out of a surface. So if you went back to that basic understanding of flux, you'll notice that 1, 2, 3, 4, 5 electric field lines went into the surface, but 1, 2, 3, 4, 5 field lines came out of the surface. Net number of field lines is 0, so the net flux is 0. The other way you could have thought about it is looking at Gauss's law and saying that if there's going to be a net flux, that means there has to be a charge enclosed in the surface. Well, there's no charge in here, and therefore the net flux through that surface has to be 0. Let's look at this one. Shown below are 3 concentric spherical Gaussian surfaces, A, B, and C, with a positive charge plus Q at the center. A second but negative point charge, negative Q, is enclosed only by surface C. Which is a true statement about the magnitudes of the electric flux through the 3 surfaces? So go ahead, pause the video, and figure this one out. Okay, so again, we're using Gauss's law. The flux is equal to the charge enclosed divided by epsilon naught. Also remember that the Greek letter phi we use to represent flux. And so if we look at the flux coming through surface A, it's just related to the charge enclosed by the surface. So you'll notice that the flux through surface A is just Q over epsilon naught, because that's the charge enclosed divided by epsilon naught. If we look at the flux through surface B, notice the flux through surface B is the same because it still encloses just that charge Q, so we've got Q divided by epsilon naught. If we now look at surface C, though, you'll notice that the flux through C is 0 because the total charge within that surface is plus Q minus Q. And therefore, the correct answer is A equals B greater than C. A cubic Gaussian surface with 1 meter on a side is oriented with 2 horizontal and 4 vertical faces as shown. It is in a uniform electric field of 20 newtons per coulomb, which is directed vertically upward. Choose all of the following statements that are true. So go ahead and pause the video and see if you can figure this one out. Okay, the correct answer is C. Both of these statements are correct. So let's go through and make sure that we understand that. First of all, you'll notice that simply the number of field lines that come into the surface equals the number of field lines that goes out. So definitely the flux through the whole cube is 0. But now we're asked to figure out the magnitude of the flux through the top of the cube. So let's actually calculate that. We know that as long as the electric field is constant over the surface, the flux is just E dot A. And we know we calculate that by taking the magnitude of the electric field, the magnitude of the area, and the cosine of the angle between the vectors. So notice in this case, the electric field is 20 newtons per coulomb. The area of that top surface, since it's 1 meter on a side, is just 1 meter squared. And then the surface area vector at the top would just be straight out. Notice that's the same as the direction of the electric field vector. So it would be cosine of 0. And that would give us a flux through the top surface of 20 Newton meters squared per coulomb. Notice, by the way, if we had calculated the flux through the bottom, what we would have found is there, the surface area vector is down, right, out of the surface. Of course, the electric field vectors are up. And so you'll notice that the flux through the bottom of the cube only changes because theta would now be 180 degrees for the bottom. And so the flux through the bottom surface is negative 20. There is no flux through any of the sides, and therefore 20 minus 20 gives us the net flux through the cube of 0, which we already knew. And so both statements are correct. Okay, that concludes our study of Gauss's law. Again, key things to remember about Gauss's law. First of all, the surface that we're talking about in Gauss's law is an imaginary surface that you draw. If you want to be able to use Gauss's law to just find the flux, it doesn't really matter what surface you draw. Just draw a surface, add up the charge enclosed, divide by epsilon naught, and that's the flux. But flux isn't really a useful quantity on its own. The quantity that's useful is the electric field. If we want to solve for the electric field, we've got to be able to get rid of this integral. And the only way that we do that is we have to pick a surface over which the electric field is constant. And that's how we can go from the integral of E dot dA to just EA cosine theta. If there isn't a surface over which we can make the argument that the electric field is constant, then Gauss's law is still true, but we can't use it to solve for the electric field.